Thank you very much. It's a great pleasure to be here this morning in Frankfurt with you to bring you the latest science. And I want to start with a quote by Alexander von Humboldt. This wasn't agreed with Fritz beforehand, but it's one of the great German holistic systems thinkers of the 19th century. And I like quoting him not only because I went to Alexander von Humboldt High School in South Germany, but he is simply one of the great science heroes here in Germany. And he wrote in 1843 already that humans are changing the climate, quote, by cutting down forests and by releasing large amounts of steam and gas at the centers of industry. Humboldt may well have known the greenhouse effect because that was described first by Fourier in 1824. But Humboldt certainly didn't have a detailed understanding of the Earth energy budget as we have it today. Based on measurements, we have a global radiation measurement system on the ground. We have satellites that measure the incoming and outgoing radiation at the top of the atmosphere. And I won't go through this diagram in all detail, but on the left in the yellow, you see the shortwave radiation. That's the incoming solar radiation and the reflected parts of that. And in orange, you see the long-wave radiation that is emitted by the Earth, but also partly trapped in the atmosphere because the atmosphere is transparent for the shortwave radiation, but not for the long-wave radiation. That was first demonstrated in 1859. So a lot of the radiation, the heat we try to put back into space comes back as back radiation, which you see at the bottom right. And that is exactly the greenhouse effect. 340 watts per square meter are arriving here. And as you see, it's twice the amount of solar radiation absorbed at the Earth's surface. So when we are turning the knob of the greenhouse effect, we are basically turning the biggest knob in the radiation budget of our planet, which determines the global temperature. The problem here is that we have increased the amount of greenhouse gases in the atmosphere dramatically. This shows this for the last 10,000 years, the Holocene, and you see the dramatic rise in the most important greenhouse gas that we are increasing, namely carbon dioxide. And that rise is accelerating, as you can see here. That increase is completely caused by human activities. That has been shown already since the 1960s. And what we have done so far has changed the radiation budget of the Earth by 2 watts per square meter of Earth's surface. This is where the energy comes from that is heating up our planet. The result is this. This is a picture of global temperature increase. Every stripe is 1 year of global temperature, starting in 1880 here, famous warming stripes. Conventional view of these data is shown in this curve here. And it shows that we have seen an increase of 1.2 degrees centigrade globally since the late 19th century. This modern warming is completely human-caused. Often you hear humans have contributed to modern global warming. Well, in fact, we have caused it. And you see here from the latest report by the Intergovernmental Panel on Climate Change, published earlier this year, the comparison between the independent measurements of how much warming we observe and estimate how much human-caused warming there is due to these changes in the Earth radiation budget that we are causing. And these bars simply have the same height, and it means 100% of modern warming is human-caused. Only plus or minus 0.1 degree have been caused by natural drivers like changes in solar activity or volcanism, where solar activity actually has declined over the last 60 years and slightly counteracted the warming that we are causing. If we compare this to the last 20,000 years of Earth history, which we can do because we now for decades have collected sediment cores, ice cores, etc., in enough places around the globe to determine the past global temperature evolution, we see that here we first see the transition from the last ice age, 20,000 years ago, into the Holocene, a warming by about 4 or 5 degrees warming, and then rather stable Holocene climate. And we have dramatically turned this round since, because of that modern warming, and we have already left the natural variation range of the Holocene. We are catapulting ourselves basically out of the experience of the entire period of human civilization, which started about 10,000 years ago with the invention of agriculture and humans becoming settled and starting to build cities. Very likely we're now already above any temperature globally which has been experienced throughout the Holocene. If aliens observe us from space, they would also see what's going on here just by looking at the North Polar Cap, the sea ice cover on the North Polar Ocean. And this is what it looked like in the 1970s and 80s up until then. By now in the summer it typically looks like this. And I think most people in the audience will still see this situation where for the first time we have basically ice-free polar ocean in the summer. If we look at the time series of this, here's again based on sediment data from the Arctic, the last 1,500 years of sea ice cover on the Arctic Ocean. We see it's kind of been pretty stable, and then it's just been going downhill. And this adds the recent observations starting in the 19th century to those sediment data and the satellite trend that we have since the 1970s. So we see a dramatic decline. The sea ice cover has been cut by almost half, and also the thickness has been cut in half. So overall we have only about a quarter of the amount of sea ice on the polar ocean in summer compared to what it used to be. What humans mostly feel is the extreme events, not the annual average temperatures or anything like that. And if we look at heat records, they obviously have increased as a result of global warming. Any layperson would, of course, expect that. And maybe you wouldn't expect that monthly heat records have already increased 8-fold. And of course, each record is higher than the previous one, so that not only the number of records has increased, but their temperature has increased at the same time. And for example, in Europe, the hottest summers since the year 1500 AD have been 2021, 2018, 2010, 2003, and 2019. You don't need to hire a statistician to tell you that this is not a random distribution, but clearly a result of the massive warming trend. And as a reminder, heat waves are silent killers. The European heat wave in 2003 has caused 70,000 fatalities in Europe. You can see that, for example, here in the mortality statistics of France. The annual course here is shown. All the gray curves there are the past years of the past decades, and the blue curve is the year 2003, which had the by far highest mortality peak in the last 50 years since this statistic exists. A peak that was even higher than the 2020 corona fatality peak in France. Also, rainfall is increasing because of simple physics. Warmer air can hold more moisture. It's a basic law of physics, of course, the Clausius-Clapeyron equation, which determines the saturation vapor pressure as a function of temperature. And it leads to rainfall extremes increasing strongly. And if you look at short-term, like daily rainfall events, it's something like this, which we have seen in the town of Braunsbach a few years ago in Germany, a flash flood. These flash floods are simply increasing due to global warming. It's not just a prediction, this is an observed fact, and it's also been observed in Germany, in Holland, etc. In the last IPCC report has said in Central and Northern Europe there is a significant increase in extreme rainfall events. And here's a study from the ETH in Zurich of 2020 showing that also in Germany extreme rainfall has been on the rise. That's events like the one that we have seen this summer in Germany, causing a catastrophic flood with about 170 people dying. And also subsequently a specific attribution analysis for this flood has shown that the likelihood of such a disaster occurring has increased very strongly due to global warming. On the other side, we also see an increase in drought, which again has to do with that Clausius-Clapeyron equation and the fact that more and more of the overall rainfall that falls, which is ruled by how much evaporates from the oceans in the long term, a greater percentage of that is falling in extreme rain events, and less water is left for kind of normal rain, and we have longer drought periods as well. The United States, the Western USA are in a record drought state this summer. That has contributed to the massive fires that you see on the satellite image, where the smoke has blown across the entire United States, even causing air quality issues in New York City on the other side of the continent. In Europe, the main drought problems are in the Mediterranean region. We have been also predicting this for decades, and we now also observe this already for many years, that this drought is getting worse there, also leading to big fire problems, but also to harvest failures, like in Syria. Some people may know that Syria suffered the worst drought in its history in the years leading up to the mass protest and unrest there. And according to sediment data, this was probably the worst drought in at least 900 years in the region, leading to farmers having to leave their villages. 1.5 million interior refugees within within Syria, which have increased the dissatisfaction with the Assad regime. And nobody says they were the only reason, but they have contributed certainly to the political unrest there, and we all know where that ended up. Tropical cyclones have also been long predicted that they would get stronger because they draw their energy out of the warm upper ocean, the heat energy stored there, and now also the satellite data clearly show this increase. The major hurricanes, those are the ones of category 3 and above, which cause most of the damage, have increased their share from around about 30% to nearly 40% of all tropical cyclones now. Another inevitable physical consequence of warming is sea level rise, because water expands when you warm it, and continental ice sheets melt as they are warmed, and we see this sea level rise. We also see that it's accelerating because ice is melting faster the warmer it gets. That's another very obvious fact. And the Intergovernmental Panel on Climate Change in the latest report says that by the year 2100, we can't even rule out 2 meters of sea level rise, and by 2150 we can't even rule out 5 meters of sea level rise, depending on how the big ice sheets start to respond dynamically by ice sliding, etc., to this warming. And we have to be aware that currently we still have enough ice on Earth to raise global sea levels by 65 meters. Even 1 meter would be catastrophic for many coastal areas. So far, we have seen 20 centimeters of rise, which already is causing serious problems in some areas with nuisance flooding, increased storm surge problems, etc. And Earth history is a stern warning about this. At the end of the last ice age, which I showed earlier on, about 4 to 5 degrees warming, we saw 120 meters of sea level rise. And what this means for places like that is pretty obvious. This is Male, the capital of the Maldives. Another issue that is increasingly debated not only in the media, but also in the IPCC report, is the question of tipping points. And since it's often misunderstood, I want to say a few words about that. This picture actually illustrates quite nicely what a tipping point is, because it shows a ball in this bowl, and if this person pushes it a little bit to the side, it will roll back to the deepest point there. But if you push it beyond this particular point, it's not going to roll back to its original place anymore. It's going to continue rolling off to the right-hand side there. And that is exactly what a tipping point is. These tipping points occur in many physical systems. All you need for that is an amplifying feedback, so some non-linearity in the system. And the tipping point is basically a point where the further evolution will be self-amplifying, and the system goes over into a completely different state without you pushing it any further. And the climate system is full of such tipping points. We published an overview in the top scientific journal Nature 2 years ago on this, looking at various tipping points like the ice sheets. They have well-known tipping points. The Atlantic Ocean circulation is a tipping point known since the 1950s. Ecosystems like the Amazon rainforest, for example, they have their tipping points because they can only sustain a certain amount of pressure, for example, drought, until forests die, for example. So this is very well established. And what is becoming increasingly clear in the science, and we have a big project on this at our institute as well, is the interaction of tipping points. For example, Greenland melting releases fresh water into the North Atlantic, which weakens the Gulf Stream system, the North Atlantic circulation. And what we concluded in this article is that the clearest emergency of a planetary scale would be if we trigger a cascade of tipping points, which, like dominoes, one of these tipping points triggers the next. This would really be kind of a nightmare scenario, but it's not unrealistic. So let's talk about what to do about this. And thankfully, we have the historic agreement, the Paris Accord of 2015, reached after decades of negotiations since the Rio Climate Summit in 1992, which started off that whole process. And the goal is to hold the increase in global average temperature to well below 2 degrees above pre-industrial levels, and to pursue efforts to limit the temperature increase to 1.5 degrees above pre-industrial levels. And now the race is on to fulfill what was agreed by all nations in Paris. And many people ask, is it even still possible to limit warming to 1.5 degrees? And the answer is yes, it is still possible. Some people think that warming is already baked in by past emissions, which would push us past the 1.5 degrees, but that's not what the latest science says. It does say that once we reach zero emissions worldwide, temperature will probably stop to rise. It might rise a little bit further, but equally likely it might start to drop slightly. The average of all the many model simulations that have been done on this is that we basically stabilize global temperature once we have achieved zero emissions. And as you see on the current trend, we'd reach the 1.5 degree limit sometime in the 2030s. The latest IPCC has it a little bit earlier than I sketched here just by this linear trend analysis. But if we start reducing emissions now and cut them in half by 2030, we will slow down this trend, and we kind of can hit the brakes just fast enough to stop at about 1.5 degrees. This is just a very rough flash of policy measures that can get us there. Kind of rule of thumb, cut emissions by half every decade, and also ramp up a little bit of CO2 removal so that we can get rid of some remaining small emissions that we simply cannot get rid of, for example, from agriculture. It's from a paper by Johan Rockström from 2017, but the basic measures are still the same as are debated today. And of course, ending subsidies for fossil fuel use, including hidden subsidies that are simply arising from the damage costs not being priced in there, ramping up renewables dramatically, and so on. I think you probably all have heard this in many different versions. The key point I want to make here is that the amount of global warming which we will get depends on our cumulative emissions, so the total CO2 that we have emitted since the beginning of the Industrial Revolution. And that means we have a limited emissions budget to still spare, and the later we start reducing, the earlier we have to be at zero. This is what this diagram illustrates, and so waiting is absolutely no option, not anymore. And also the emissions budget that we can still afford is a very tiny part of the fossil resources. So spending a lot of money looking for more resources is just basically stupid from my point of view, since we have to leave by far most of that in the ground anyway, so-called unburnable carbon, or in financial terms, you'd probably call that stranded assets. So let me conclude. Global warming is unequivocal. That's already a statement from the IPCC of many years back. It's ongoing. We're in the middle of it. It's not some kind of prediction. The impacts are not subtle. Many millions of people around the world are suffering from that already. Stopping global warming well below 2 degrees, as agreed in Paris, let alone at 1.5 degrees, is really a race against the clock now to reach the zero emissions. And so far, the commitments of governments to this are far too weak, and every year counts because of many years or decades spent on dithering. With that, I thank you for your attention, and I'll be very happy to answer some questions.